Have you ever noticed that hum coming from your computer? You know, those little fans whirring away inside your laptop, maybe your desktop. And it's not just one or two, right? Often there are several. You've got them for the power supply, the CPU, the graphics card. Seems pretty simple, but those fans, well, they're actually guarding this really fascinating secret about how electricity and heat interact, especially in these complex devices we use every single day.
It's absolutely true. There's a really crucial connection there between temperature and how electricity behaves, sometimes quite surprising. And actually, today's deep dive is inspired by some great insights from Jun Byung-chul from his book Jaejin Chobo Juryoma Jungji, which translates roughly for you as Beginner's First Steps in Electricity. It's published by Gilbert Publishing, and honestly, it's a fantastic resource for getting your head around these fundamental ideas. Really makes it accessible.
Right, and that's exactly our mission for this deep dive. We want to unpack that essential relationship, temperature and electrical resistance, and explain it hopefully in a way that makes perfect sense even if, you're just starting out with electronics like the book aims to do. We want to figure out why those cooling fans are so incredibly vital for the tech in your life. Okay, let's dig in. So we all basically get that fans cool things down. You see them everywhere, car engines, big industrial motors, places where overheating is obviously bad. It can, warp metal, seize up parts, mechanical stuff.
Exactly. Overheating can fundamentally change the properties of materials in those systems.
But here's where it gets really interesting for electronics. If cooling is so vital for mechanical things, why are there so many cooling fans, specifically in electronic products, like computers? It feels like a different sort of problem, doesn't it?
It does, and the answer really lies in understanding how electronics specifically react to heat.
And our sources point towards something called the temperature coefficient.
Yeah.
That's the key.
That's the core concept, yes. But first, maybe just a quick refresher on electrical resistance, to make sure we're all on the same page. Put simply, resistance is just how much a material sort of pushes back or impedes the flow of electricity.
Like a narrow road for traffic. Or maybe a bumpy one.
That's a great analogy, yeah. And while resistance definitely depends on the material itself, how thick it is, how long it is, the really crucial thing here is that this electrical road, as you put it, it also changes characteristics with temperature.
Ah, okay. So it's not just about how wide the road is permanently, but how hot it gets could also change the traffic flow.
Precisely. And that brings us to this term, temperature coefficient of resistance. Basically, think of it as a material's sensitivity dial for heat. It tells us the ratio, how much the resistance increases compared to its original value when the temperature goes up by just 1 degree Celsius.
Okay, so a higher coefficient means it's more sensitive. A small temperature change has a bigger effect.
You got it. A larger temperature coefficient means resistance reacts much more dramatically to temperature shifts. And what's really fascinating and kind of the crux of the matter for computers is how different materials react. They can be polar opposites.
Right. This is where, as our sources suggest, it gets genuinely surprising. Different materials heating up.
Yeah.
They behave in completely different ways.
Exactly. Let's start with the one that probably makes intuitive sense. Metals. For most common conductors, think copper wires, the kind you find everywhere. Resistance increases as the temperature goes up.
Okay. Hotter means harder for electricity to flow.
Correct. So the book gives this example. If a copper wire has a resistance of, say, 10 ohms at 20 degrees Celsius, if it heats up, its resistance will become more than 10 ohms. We call this a positive resistance characteristic. Positive because temperature and resistance go up together. They're directly proportional.
Makes sense. Hotter wire, more resistance. Got it.
But now, the twist, and this is where it gets really interesting, especially thinking about your computer, semiconductors. Semiconductors are the absolute building blocks of, all modern electronics. CPUs, memory, everything. And they behave completely differently from metals when it comes to heat.
Differently how?
Unlike metals, for semiconductors, resistance actually decreases as the temperature goes up.
Wait, decreases?
Yeah.
So it gets easier for electricity to flow when it's hotter?
Yes, exactly. Current actually flows better, more easily through a semiconductor when its temperature rises. It has a negative resistance characteristic.
Hold on, that sounds counterintuitive. If current flows better, wouldn't that be like a good thing? Maybe make things faster? Why is that a problem? I always assumed heat was just universally bad for electronics, full stop.
That's a really sharp question. And you've hit the absolute core of the danger. See, your computer is just packed, absolutely jam-packed with countless tiny semiconductor components all working together. And as the computer operates, especially when you're doing something intensive like gaming or video editing,
Yeah, it gets warm, sometimes really hot.
Exactly. Its temperature naturally rises. And because those semiconductors have that negative resistance characteristic we just talked about, their resistance starts to drop, sometimes significantly as they heat up.
Okay. Resistance drops. Some more current flows.
Far too much current. This decrease in resistance basically opens the floodgates. It allows way more current to flow through those very delicate circuits than they were ever designed to handle. It's a dangerous surge, and we call it overcurrent.
Overcurrent, like an electrical flood, you said.
Mm.
So what does that actually do to my laptop or my phone? It sounds bad, like a runaway train.
It is bad. It's precisely like a runaway train for the electronics. That overcurrent can cause serious, often permanent damage. It can fry components, lead to malfunctions, drastically shorten the lifespan of your device, or even cause it to fail immediately.
Wow. Okay. So that seemingly simple heat issue is actually creating a risk of electrical overload because of how semiconductors work.
You've nailed it. And that is precisely why cooling devices, those fans, are installed in computers. They aren't just there to make it comfortable on your lap, though that's a side effect. They have sensors, they constantly monitor the internal temperature, and they activate specifically to keep that temperature stable to prevent the resistance from dropping too low, and therefore preventing that destructive surge of overcurrent.
So the fans are basically acting like safety valves,
Where?
preventing that electrical flood triggered by heat in the semiconductors.
That's a perfect way to put it. They are essential guardians. They maintain stable circuit operation and prevent damage.
So what does this all mean? The fans aren't just blowing hot air. They're vital for the very survival and stability of your computer's brain. It really changes how you think about that hum, doesn't it? You hear that fan spin up, and now you know. It's dealing with this incredible paradox, this counterintuitive way semiconductors handle heat. Those humble fans are actually sophisticated, silent protectors fighting this hidden battle inside. It's pretty amazing when you break it down.
It really is. And, it raises a bigger question, something for you to maybe ponder. Given these fundamental properties of materials, like how metals and semiconductors react so differently to heat, what other hidden battles, what other clever engineering tricks are constantly happening inside the technology we use every single day, just to keep it all functioning smoothly, reliably, without us even noticing?
That's a fascinating thought. All the unseen challenges being managed behind the scenes. It really makes you appreciate the depth of understanding, that grasp of basic physics that underpins even the device you might be listening to us on right now. So next time you hear that fan whirring, you'll know it's not just hot air. It's a critical part of this intricate electrical dance, making sure your technology keeps working.